Hi everyone, welcome back. In this particular review, we're going to start talking about protecting groups for alcohols. And to understand what these are, we'll have to first understand when we would need them. Okay. And so what we're going to do is I'm going to use the example of the reaction between a Grignard reagent and a carbonyl compound to make you to set the stage sort of. Okay. So let's assume that we have a carbonyl compound, but this compound has an additional functional group in it. Okay, so there is a carbonyl group in it, there's a ketone group, but additionally, this molecule has an alcohol group in the compound. And what we want to do is we want to react this compound with a Grignard. So let's say we have ethyl magnesium bromide. That's our Grignard reagent. And recollect that Grignard reactions are done in steps. So first, the Grignard reagent is reacted with the carbonyl compound using an anhydrous solvent. THF is a great example of a solvent that's used for Grignard reactions. And then in a subsequent step, you do an acidic workup, okay, to get to the product. Those would be the conditions. But now if we evaluate the reaction here, we have the Grignard reagent, which we've learned is a strong nucleophile, but it's also a strong base. So as far as the Grignard reagent is concerned, and as far as this given carbonyl compound is concerned, the starting material is concerned, the Grignard reagent has two options here. One possibility is that the Grignard reagent would go and attack this carbonyl carbon, which is the desired reaction, what we want, or the reaction that we would like to happen. Okay, and then the double bond would move up to that oxygen atom. So that's the desired reaction. But the problem with this substrate or the starting material that we have here is that there is an additional functional group. There's an alcohol functional group here. And since a Grignard reagent is a strong nucleophile and it's a strong base, right? So this is a nucleophile, like the nucleophilic attack, the Grignard reagent acting as a nucleophile, but the Grignard reagent can also act as a base, which means it can go and deprotonate this alcohol, the hydroxyl group. It will do that. This is when the Grignard reagent is acting as a base. And so we have two competing reactions here, the nucleophilic attack and the acid-base reaction, where the alcohol serves as the base. And acid-base reactions are fast. So kinetically, these reactions are going to be favored. So that means in this particular scenario, when you take this carbonyl compound and you react it with the Grignard reagent, the only reaction that's going to happen is going to be the reaction between the acid, or the preferential reaction that would happen is the reaction between the Grignard reagent as a base and this hydroxyl group as an acid, okay? Which means if this is the reaction, if this does not happen, okay, if that does not happen, and if this is the reaction that happens, then after the first step, what I'll get is C double bond O, so that carbonyl group stays, nothing happened. This oxygen is deprotonated. We have a negative charge over there, and this negative charge would be balanced by the MgBr. Okay. Along with that, the ethyl group picked up a proton from here. So we get ET and H, which is basically ethane, C2H6. That's what we've got there. Okay, so this is the intermediate now, and we're done with the first step. And so when you do the second step, which is the hydrolysis part of it. Okay, so this was the first step, and now we are doing the second step. So when you do the hydrolysis on this intermediate, what's going to happen is this O minus is going to get protonated again. It will pick up the proton because that's the base. It will pick up the proton from the acid. And so what we will get in the end is our starting material. We get back, or we get our starting material back at the end of this reaction. So that means we did not do anything fruitful here. Okay, we wanted the Grignard to go and attack the carbonyl compound, but that did not happen because of the presence of this hydroxyl group. So then the question is, how do we fix it? And what is the problem that we need to fix here? So when you look at it, the issue here, okay, the problem here is the presence of this hydroxyl group. If this hydroxyl group was not present in this starting material, then the Grignard would have gone and attacked that carbonyl compound, and it would have given us the product that we wanted. Now, let me put the product that we would have, or the desired product, what we were trying to make here. If the reaction proceeded the way we wanted it to, I think the product that we would have gotten is this tertiary alcohol. That would have been the desired product if the reaction proceeded the way we wanted it to. But because of this hydroxyl group, the reaction gets complicated. Okay, so now if you want to avoid this undesired pathway where the acid-base reaction happens and then the protonation happens, what we need to do is we need to get rid of this hydrogen, because that's the culprit. If we get rid of this hydrogen, then there won't be any acid-base reaction. How do we do it? So that's where the protecting group comes in. Okay, so the way we do this is, I'm going to erase some of this and rewrite, show you how the protecting group works. Okay, so this reaction would not work. And the way we could achieve this reaction is by using a protecting group. And erase this. Okay, so protecting groups for alcohols. These are silyl groups, which is basically silicon containing compounds. Okay, so silyl groups are used as protecting groups for alcohols, silicon containing compounds. And these compounds, the general formula for these compounds is R3SiCl, where R is an alkyl group. Okay, R is an alkyl group. So this compound here is basically a trialkyl silyl chloride. Okay, that would be the name of this compound, trialkyl silyl chloride, but the general name of this compound. Now, a specific example of this could be trimethyl silyl chloride. Okay, trimethyl silyl chloride. And the reason we are able to use these silicon containing compounds as protecting groups for alcohols is because silicon has a high affinity for oxygen, okay, which means it likes to make bonds with oxygen. So silicon oxygen bonds are like one of the strongest bonds. And the reason for, and a classic sort of application of this or a manifestation of this is sand. Sand is basically silicon oxide. which contains a lot of silicon and oxygen bonds in it, okay? So silicon has a high affinity for oxygen. So the way we protect an alcohol, and I'm going to use the example that we had prior, is to start with your compound. And again, I'm using this compound, but you could apply this to any alcohol. So use this compound as an example of an alcohol where the R group is all of that. That's your R group, okay? So when you have an alcohol, you react this with the silyl chloride, and we'll use the specific silyl chloride, trimethyl silyl chloride, in presence of a base. Triethylamine is a classic base. Now, this is not the only base, but that's a classic example of a base that's used for these reactions. So when you do that, what happens is you replace this H with the R3SI, the silyl group. Get OSiR3. Okay, and pretty much what you're losing here is HCl. You're losing this H, the hydrogen from the alcohol group, and the chlorine from the silyl group. Okay, so you get this intermediate. This is a silyl ether, this functional group here. Okay, that's called a silyl ether because you have an oxygen that's between a carbon and a silicon. So it's like an example of a silyl ether. Okay, now by doing this, what we've done is we've protected this hydroxyl group by converting it into a silyl ether. Okay, once we've protected the alcohol by using the silyl ether or the silyl chloride to convert it into a silyl ether, now we can go ahead and do our Grignard reaction. So now if I react this protected compound with the Grignard and follow it up with an acidic workup or a water workup, if I do that, what I'm going to get is the tertiary alcohol here. I'm not going to go through the mechanism of the Grignard reaction itself because we've looked at that before. Okay, and we will have the silyl ether group over there. Okay, but now the issue is we started with an alcohol, we protected the alcohol. Okay, so this is the protection. Okay, this is the protection that we did. This is the protection step. We've protected it, made it a silyl ether. We did the Grignard reaction that we wanted to, because now in this particular case, this Grignard is going to go and attack this carbonyl compound that would push up, and then you go through the mechanism to make that alcohol. So we got the desired reaction to happen. But the issue is now our molecule is different, right? We started with an alcohol group here, and now we're stuck with an silyl ether. So how do we get rid of that? It's possible, and what you have to do is you have to do what's called a deprotection. Okay, so we protected, and now we have to do a deprotection. Step. And for doing the deprotection, you use fluoride, some source of fluoride, like tetrabutyl ammonium fluoride, maybe. So TBAF, you might see compounds like that written. Okay, so TBF, but it's like basically some source of fluoride. You use that, and you could do it in like an aqueous medium or in a mixed aqueous medium. Okay, you do that reaction. And what that does is it would cleave this silyl bond again, the silyl ether bond. So that when you cleave that, That was our silyl ether. And when you cleave it, you will get the alcohol, the ethyl group, and you will get the hydroxyl back. So you get your alcohol back. And the reason here is that, okay, silicon has a high affinity for oxygen, okay, but it has an even higher affinity to make bonds with fluorine or fluoride. So when it sees the fluoride is going to go and attack the silicon, and it will let the oxygen go away. And so you can get rid of that silicon protection. And then the oxygen picks up a hydrogen from the water or the aqueous solvent that you're using, or through like an acidic workup later. But either ways, you can protect and deprotect. And what we can achieve by this is we can actually do a Grignard reaction on a substrate which had an acidic proton. Now, something like this protection, right now we are talking about specifically alcohols, but the reaction of Grignards with any substrate that has an acidic hydrogen in it, it's going to result in an acid-base reaction. But the silyl protection does not, it's not a universal protecting group. So it won't work for like any functional group where there are hydrogens present. There are different functional groups for different there are different protecting groups for different functional groups. The silyl protecting group is specific for alcohols. Okay, so the silyl groups are specific for alcohols. They are not universal protecting groups. Let me show you another example of where a protecting group might be needed here. Okay, and we're going to look at a slightly different scenario here. So let's say we have a molecule which is a bromo alcohol. Okay, it has a bromine functional group and it has a hydroxyl functional group. And what we want to do is we want to react this with a carbonyl compound. And again, I'm just using an example of a ketone here. Okay, it does not have to be a ketone. It could be an aldehyde. Okay, and what we're trying to do here is we want to take these two compounds and we want to convert them into into this molecule here, okay, where this carbon is now connected to that carbonyl carbon, okay? So that means this carbon needs to go and attack that carbonyl carbon. And since this is an alkyl halide, at least this part of the molecule is an alkyl halide, one strategy to do this would be to convert this into a Grignard. So I can react this with magnesium in presence of ether, okay? And in principle, we should be able to make a Grignard here, because recollect that Grignards are made by the reaction of alkyl halides with magnesium. That's how you make a Grignard reagent. Okay, so we should, in principle, be able to make a Grignard like this. But look at this Grignard. There's a Grignard reagent on one end, which means this carbon here is negatively charged. Okay. I mean, because understand that that's how the bonding is. There's a negative charge over there. Okay, so there's a nucleophile, strong base. And within the same molecule, there is a hydroxyl group. So when you make a Grignard like this, it is very likely that one molecule of this Grignard could react with another molecule of itself where the Grignard does an acid-base reaction. Okay, they will do an acid-base reaction among themselves, and when you do that, you're going to be killing the Grignard. So there's this acidic proton present in your Grignard reagent that you're trying to synthesize, and that means you would not be able to synthesize that Grignard reagent efficiently. So how could we solve this issue here? We will use the protecting groups again. Okay, so we can use protecting groups here to help with the situation. So now, instead of making a Grignard out of this bromoalcohol directly, what if I took this compound and I reacted it with trimethyl silyl chloride in presence of a base, triethylamine? What that's going to do is it's going to protect this hydroxyl group. So what I'll make is Br Me3Si. So I make this silyl ether protecting group. Okay, so that silyl group is now protecting the alcohol as a silyl ether group. And again, remember what's lost here is a molecule of HCl. That Cl and the hydrogen from the alcohol, that's lost. So we made the protecting group. And now from here, I could make the Grignard now, because if I react this with magnesium and ether, now I can make a Grignard reagent. And this Grignard is going to be stable, okay, because we got rid of that hydroxyl group, which was, or the hydrogen, the acidic hydrogen, which was there previously. So we've synthesized a Grignard reagent. And now this Grignard reagent can react with our carbonyl compound. Okay, will react with our carbonyl compound. So this carbon is the negatively charged carbon, so it can go and attack, open it up. And I'll just walk through the mechanism here as to what's going on. So we get that product. And again, these are all steps. So now we will have the O minus, the alkoxide. And over here, we're going to have the OSI Me3, that protecting group. And now the Grignard, so these are all individual steps. So as we do in every Grignard reaction, we're going to quench it or do a workup with an acid. So this is a separate step now. So when we react this with an acid, this alkoxide is going to get protonated. That will give me a hydroxyl group up there. And the silyl protection is still there. And now notice how the silyl protection can be removed using the fluoride treatment. Okay, so when we react that with the fluoride, it's going to give me the alcohol, or give us the alcohol and the alcohol here. So when we do that treatment, okay, so we get rid of that, and then the silyl protection falls off. So that way, what you can notice is we can actually synthesize that compound, which we would not have been able to synthesize otherwise, right? Because we had this issue where our starting material had an acidic molecule. The alkyl halide had an acidic proton in it, an acidic functional group in it. So the acidic proton would have messed up the Grignard synthesis. But by going through a protection and a deprotection strategy, we could actually get rid of, we could actually make this synthesis possible. Okay, so we did the protection here. And we did the deprotection in the end. Okay, so I hope those examples sort of help you understand the use of protecting groups specifically for alcohols.